Okay, time to move into a new chapter looking at properties of materials and effects of forces and things like that on materials. And so we have some new equations here. We'll go through a little more detail here in a minute, but just to get the equations on your equation sheet. So new terms: stress, sigma, force per unit area. Units will be PAs, which are pascals, right, which is similar to, or it is the unit of pressure also, the SI unit. Strain is another new variable. Basically it's a change in length divided by the original length. For tension and compression, we got delta L over L, and for shear, we've got delta X over L. So this is basically a unitless thing. It's like meters over meters kind of a thing. We're going to have some variables we call various kinds of modulus. Their units are going to be pascals, but they're going to be, so we have three that we're going to look at. We've got elastic modulus, which is also Young's modulus. You can remember it's Young's modulus because we're calling it a capital Y. And all of these are stress over strain kind of things. And so when we're talking elastic modulus, we're talking things that are compressed or stretched. And so we're going to have stress, F over A, over its strain. For shear modulus, we're going to call it capital S. And so different materials will have these different, have a modulus, a shear modulus, an elastic modulus, bulk modulus for each different, like iron or steel or whatever, different kind of material will have its own modulus of these different types. All right, so in general, stress over strain. And so, so the bulk modulus, I guess I didn't write down the bulk modulus formulas, but the bulk stress is going to be the delta P, the change in pressure, where pressure again is like strain. It's got the same formula, pressure per unit area. And then the bulk strain is a volume measurement instead of a length measurement. So change in volume over the initial volume, and capital B for the bulk strain, and we've got this negative added in here for the volume change, or a coefficient of the bulk strain. And then there's just in general, the pressure formula is the same as the stress formula, force per unit area. And lots of times when we talk about pressure, we're thinking about a fluid, a fluid which is a liquid or a gas being compressed or uncompressed, whatever. Okay, so those are the equations for today. All right, so we're talking about elasticity of materials. So if you think about elasticity of materials, and so if you think about things like steel or concrete or copper or what have you, you might not think of them as being very elastic. But what we mean by a material that is elastic, it means that it can be deformed. Okay, so things, maybe diamond is really hard and can't be deformed very well, but they can be deformed. So you put enough force on them, you squish them hard enough, or you stretch them hard enough, even though they seem pretty solid, like steel or what have you, it can be stretched with enough force, right? So stress, then, like we saw in the equation, we're calling it sigma. Stress, sigma is force per unit area, force over area. And maybe the easiest example, well, two easy examples, I guess, but if you think of a force pulling on a cable or wire or something like this, then we've got the area. If this is like cutting a cross section and seeing the force inside the cable, the area would be the surface area of the cable, right? And so the force, we'll think of the force acting over that whole area. So the stress is the force over the area, right? We would tend to call this tensile stress, right? It's the stress of tension, the stress of being stretched, okay? What are the units of stress? I probably had it on there before, but it's force over area, so it's newtons per square meter, right? All right. The other one that's kind of its partner or whatever, the dual of this would be compressive stress. So we've got something and it's being pushed, being squished. All right, we've got, these are forces, the forces. So you kind of think of springs kind of things, but all materials kind of have this elastic property. And so we would call this compressive stress. Right, also newtons per meter squared, and also we're assuming that the area then is the whole area of the beam or the whatever thing is being squished, right? And so the surface area, the force is acting over the whole surface area. So we can get the stress as F over A. Okay. The last kind of stress that we'll consider is when we have something that's being, it's called shear stress. And it's when the forces are trying to kind of cause a twist. You might think of it like that. Right, trying to cause a shear. So a shear, you know, if you think of cutting shears, they cut like this, they cross over each other like this to cut things. So like one side of the scissors pushes on one side, if this was like a big expanded piece of paper, one side of the scissors pushes here, the other pushes here to cut across, so shear it off. And so a shear stress has the forces not acting in line with each other, but out of line with each other, trying to, you know, make a crack through the stuff, making it shear off and break through the middle is what it's, you know, what the material, if material can feel, what it feels like. So the top is being pushed one way and the bottom is being pushed the other way, right? So they're being sheared off, trying to shear the material off. Okay, so we would have then shear stress from that kind of application of force. Okay, so stress, force per unit area. Right? How much stress do you feel? You got forces all over you, squishing you in. That's a stress. Okay, strain. Stress and strain are talked about together quite often, so it's often hard to keep them separated. But try to figure out in your mind, or tell yourself a little story. You know, what is the difference between stress and strain? So strain is the fractional or percent deformation caused by stress. So fraction deformation caused by stress. Caused by stress. So strain is a change in length over the original. So it's a fraction of deformation. How the deformation is like the delta L. So if we have this thing that we were pulling, like the first example, and it used to be this long, but now it got longer, we've got a delta L, right? And so it's been stretched out by the forces pulling it, and so we've got a delta L, right? So it's a percent change or percent difference from what it used to be, kind of a measurement is the strain. Okay, and so same kind of thing for the squishing. If we've got something and it used to be this long, for the compressive stress, used to be this long, but then we squished it in, and now it's only this long. This is the new L. So we've got the delta L here. Right, so this would also be the this would be also the strain that is the compressive or tensile or elastic strain, right? Okay, so how much is changed in length over the length. So again, no units, length over length, meters over meters. So that part doesn't matter. All right. So that's elastic strain, or strain from tensile or compressive forces. But we can also have strain from shear, shear strain, strain from shear. And so in that case, we have a change like something like this. We've got the force forces are pushing and tend to make it bend, right? And so the L naught is the original, still the original height, but then the delta X is how much it changed this way. All right, so it's got a slant in it. So the strain from shear strain from shear is going to be this delta X now, because that's the thing that's deforming, that's the thing that's changing, divided by our original length of the thing. Okay? All right, we'll save the bulk definitions here for a little bit. But let's go ahead and look at an example here. We'll start with just the regular compressive example. There's a staple there. So let's say we have it's actually a square-shaped rod kind of thing that's holding a mass of some sort, a big mass M here, and so it's I'm going to say it's a 5 meter long rod, and it's made out of steel. So as you can guess, lots of these different moduli and parameters are published. You can look them up for different types of materials. So we're saying we have steel, has a square cross section, and so it's got 5 millimeters on each side. Yes. Alrighty. And we've got the mass here. There's a heavy mass on the end of this rod. It's welded on or something. 120 kilograms. And we're going to look for stress, strain, and stretch. Stress. All these S words. Strain. And then how much is it stretched? Stretched. Stretch. Okay. So we're looking for these things. So, of the rod. Okay? And so, let's do stress first. So stress, sigma, is force per unit area, right? What is the force on the thing? I think we're going to ignore its own mass. We're just going to look at the stress from end to end of what's caused by the heavy mass on the end. So the force then will just be M, well, we called it capital M, times G, and the area is the area that's feeling the stretch, feeling the force. So it's this length times width kind of area, right, of the little stick thing itself. All right, so let's just put in some numbers. We got 120 kilograms, and we got G 9.81, and then we've got the length and the width are each 5 millimeters. All right, so our stress is just 120 times 9.81 divided by 0.005 times 0.005, or 0.005 squared. Okay. All right, so our stress is big number, 47.1 times 10 to the 6th pascals. So it's a big number. Pascals tend to be little things. We could say, if we're being more careful with sig figs, it would be 47, and then we've got 10 to the 6th. Remember what 10 to the 6th is in terms of the metric prefixes? It's a gigapascals. 10 to the 6th pascals. All right, we're used to thinking of giga in terms of memory, 10 to the 6th gigabytes. You know, it's a million. All right. Okay, so now we want to know the strain. So what is the strain? Well, good question. How much? So the strain is going to be delta L over L naught. We got L naught, right? L naught was 5. It was a 5 meter long rod when we started, so L naught equals 5 meters. But what's delta L? Well, delta L is the stretch, right? Looks like we're going to need to know that to get the strain. So let's talk about then Young's modulus, or the elastic modulus, right? We said the elastic modulus, or Y, is stress over strain. All right, so we can get the strain then, if we want to rearrange here, is going to be the stress over Y. I don't know why I'm making my Y that way versus this way. Anyway, it's supposed to be capital Y. Okay. And so, yes. So we need to know Young's modulus for steel. So let's see if I've got that number here somewhere. Yes. So Y for steel, and there may be different ones for different kinds of steel, but looks like it's 200 gigapascals. Alrighty. And so that's a property of the material itself. Again, and this is for a certain kind of steel, but we'll assume this is, anyway, good enough number for what we're doing. All right, so then the strain is going to be sigma over Y, which is 47 gigapascals over 200 gigapascals. All right, and so 47 divided by 200, 0.235, 0.235 watts, right? It's a, it's strain, right? It's delta L over L, it's unitless, so 0.235 is the strain. Per unit, sometimes we call things like this per unit, put a little PU there, unit over unit. But what, excuse me, I just leave off the units for now. Okay, so we got strain, we didn't actually have to find delta L after all. And so now we've got strain from its kind of defining equation is delta L over L naught. And so we can get delta L is L naught times the strain. And running out of room, but delta L then, L naught was 5, and strain is 0.235, is 1.18 meters. Alright, so that's a pretty thin rod, only a 5 millimeter rod, a little skinny little rod. And it stretches 1.18 meters from longer, so it ends up being then 6.18 meters from what it used to be. Did I do something wrong here? I got something wrong here. I think there's a conversion issue. Yeah, the modulus number is, let's use, there was a conversion in the notes, but I think it's got an error. 10 to the 10th Pascal. Let's try that number instead. All right, so this is 20 times 10 to the 10th would be not 200 times 10 to the 6th. Okay, and this one is 47 times 10 to the 6th. Let's just let our calculators help us here. Let's get this right. So we'll do 47 times 10 to the 6th divided by 20, 10 to the 10. there we go, 0.235, or 235 times 10 to the negative 6. Okay, so 0.235 times 10 to the negative 3. 10 to the negative 3. All right, so that's millimeters. 1.18 millimeters. That makes a lot more sense. So stretching a whole meter was quite extreme. Okay, makes more sense. 1.18 millimeters. Okay, and so just because it seems like a strong material, if it's got enough force, it can act like a spring, or actually not like a spring because it doesn't go back. It is deformed, so it can, but it can be stretched. Okay. All right, so we've got delta L after a little bit of confusion, but we got delta L. Okay. So what do I look at next? So we talked about shear strain and shear modulus. Alrighty. Let's look into did we talk about the shear modulus? Well, let's just do an example with shear modulus, or just look at the equations just a little bit more. And so we had the shear kind of situation where we had the delta x is here, L naught here, and the forces. All right, so we said the strain is delta x over L naught, and the shear modulus was stress over strain. All right, so that's force per unit area divided by the delta x, so strain, over L naught. And so if we were, anyway, the same kind of thing, if we're looking for stress, we could rearrange this and say that the stress is equal to the shear modulus times the strain, and vice versa, which is S times delta x over L naught equals FA. Anyway, it's just rearranging of the formulas, but just realize that like most of these physics problems, we can be given one or the other, rearrange, and solve for the one we need. But the basic equation was already given, so I think we're good on that. All right, let's talk about bulk stress and bulk strain. And bulk modulus, I guess. Okay, so we're thinking of now 3D kind of material, right? And we've got forces in all directions. Get them all in here. Okay, so 6 faces of a cube. We have six directions, 6 pushes in on all directions, right? For example, pushing in or pulling out or what have you. But it causes then a 3D kind of deformation. So then the deformation in volume. So again, we have pressure is like the strain. It's like the stress is force per unit area. All right, so that's pressure P in pascals. Okay. Quite often we will think of this for a fluid like oil or gas or air in a piston. We might have something like some sort of a piston situation where you have some sort of a container, and there's a liquid or something or a gas or something in here that is compressible, and so then the piston has a force down on something is forcing the piston down, right? And so we would have a we call this delta y, delta x. We'll call this the x direction. And so, say it's, I'm not drawing very nicely here, but say we had an initial x was up here, but the piston or the force on the piston has pushed it down, so we have a delta x. And so the change in volume then, right, the volume for, so this is trying to make a 3D picture here. Volume in general is area of the base times the height, right? And so it would be, we can call it just area, whatever, times, in this case the height is, well, the height is x. If we want the change in volume, then the change in volume is going to be, well, if we're coming down, it's going to be negative, and then a times delta x. All right, because the volume is decreasing, so the negative sign. And so we've got the A is the surface area. If we want to try to draw 3D, maybe it's round or maybe it's square, whatever, it's the area of the bottom. And so then the change in volume will just be area times the change in x. All right, assuming the piston just is the same shape, just goes up and down to compress the thing. All right. So then the bulk stress is just defined as the pressure, just defined the same as force per unit area. Okay, but thinking 3D. But then we're going to tend to, in the bulk sense, we're going to tend to just call it the pressures, or the change in pressure actually. All right, so it's the extra applied pressure, not due to the atmosphere, but the pressure from the force, right, on the area. Okay, so the bulk stress, think when you're looking for or given problems with that, think about the change in pressure for the bulk stress. The bulk strain, remember the strain is how much it deforms, basically as a fraction. So we're deforming the whole volume. Somehow it's getting a smaller volume. So that's going to be the delta V over the V naught. And so we're kind of a 3D bulk sense. The bulk strain is going to be then this delta V. If it's a piston type thing where the only one dimension is changing, we can say negative A delta X. To get the bulk strain as change in volume over volume. And then finally, like we had before, the bulk modulus we're calling B is stress over strain. In this case, we're calling the stress the change in pressure, and then the strain is the change in volume. The expression we just have there. So we get, oh, and don't forget our negative sign in there, just because of that's how we're defining the bulk modulus, with a negative sign in there. Okay, so lots of paper here. We can, let's just get, I should have put this on the equation sheet probably, but the bulk modulus for water, just to get some idea, is 2.2 gigapascals. All right, so it's water is a fluid, so it is somewhat compressible, not very compressible, but more compressible than something like iron, right? Iron, 160 gigapascals for bulk modulus. But how about ethanol? A gas is 0.9 gigapascals. Okay, so the material with a large B will be very difficult to squish, very difficult to compress, right? So iron is going to be a lot harder to squish, right, than water or ethanol, right? Hopefully that makes sense for the bulk modulus kind of numbers. All right. In general, we have, like we said, we have the shear modulus. I forgot to mention, but usually the shear modulus is a little bit smaller than the elastic modulus, Young's modulus. But again, they're all properties of the material, the element, the whatever the thing the thing is made of that we're talking about, either stretching or compressing kind of thing. Okay. So let's get the bulk modulus equation back here. So we have B was delta P over negative delta V over V naught. And let's just look at a little bit of an example. So let's see. Let's say we have a closed-in vessel, some sort, very strong vessel that won't allow the volume of some sort of fluid. Maybe think of gas or something in there that won't change. All right, and so the pressure, the volume of the material cannot change. All right, we'll say that it starts with a pressure of 1 atmosphere. Okay, what's an atmosphere? Right, atmosphere is another unit for pressure, right? And so one atmosphere is 101.3 kilopascals. Doing that from memory, I think I got the right number. Pretty sure that's the right number. Okay. Might double check that just to be sure. Anyway, pascals are tiny little things. Atmospheric pressure is significant number of pascals. So lots of things are measured in atmospheres just because of the tininess of pascals. Okay, so we're going to assume we have 1 atmosphere pressure inside of our thing, and then what are we going to do to this thing? We're going to heat it up. All right, heating. So what does heating do to something? We haven't gotten to the ideal gas laws and the equations for that, but in general, we know that when things get hot, the molecules start moving faster and they want to expand, right? So it wants to, if it was an open container, the volume would get bigger, right? And let's just say that it would try to, if it was an open container, it would have a 1% expansion. Okay? So that's saying that delta V over V naught is 0.01. It would try to expand that much, if it could. But it can't, because it is stuck inside of this container. Okay, so let's use this equation up here to see then what happens to the pressure. So if we want to solve this for the pressure, if you think about it, if it's heating and it wants to expand but it can't, it's going to be under more pressure, right? So we're going to have a change in pressure, and just rearranging this is going to be B times negative delta V over V. So bulk modulus times the strain, right? With a negative sign tucked in there for fun. All right, and so let's see, we need to get some sort of bulk modulus for this stuff. I guess we're just going to say it's ethanol. All right, so we're going to say this is ethanol now. All right, and we had the bulk modulus for ethanol, which is 0.9 gigapascals. And so we're going to have delta P, which is what we're looking for, negative V, or B, 0.9 times 10 to the 6th pascals, and then a negative, so let's pull a negative sign out here, and then delta V over V was 0.01, 1% kind of a number. And so we want this in, well, let's go ahead and get it in pascals first. And so delta P is just do the multiplying, so we have 9 times 10 to the 6th pascals. Got the notes are negative. We got the well, okay, delta V over V, this was actually, we're going to get the negatives go away. So delta V over V, actually it was shrinking. Is that right? We cause it to, so by, it wants to be 1% bigger, but we're holding it in, so it's got like a 1% shrinking anyway, so we end up with a negative, two negatives make a positive. So in pascals, it's this. If we want it in atmospheres, which is what the notes wanted in atmospheres, we're going to do 1 atmosphere, 101.3 times 10 to the third pascals. And doing that conversion, we get roughly 90 atmospheres. Okay, so what does that mean? 90 times the normal pressure of air at sea level at a certain temperature, whatever, is an atmosphere. And so it's quite a lot of pressure, right? 90 times the normal pressure. And so of course, if it's heated up too much more, or if the pressure gets too great, it can break. Just like we saw the steel or whatever, they all have their own bulk modulus, and so they can handle a certain amount, and then they will fail beyond that. So definitely heard of vessels failing because of too much pressure, because a gas gets too hot. It has a lot of potential pressure. Okay, let's see. I think we're going to move on to a little bit different topic next. So let's just go ahead and stop with that, and we'll see you next time.